fundamental matrix. And what do you do? Well, I describe the solutions to any system of linear ordinary differential equations. Really? But didn't we just find out that, like, all that is just a linear combination of the eigenvectors multiplied by e to the power of t times the respective eigenvalue? Oh, it is true that my column's coefficients are the eigenvectors, and that I contain the exponentiated eigenvalues, but I have much more important. I'm a fundamental matrix. But it sounds like you're conveying exactly the same information. Oh, let him be, Fred. I'm sure sometimes it's very useful. That's right. If you want to solve for lots and lots of initial conditions, you'll wish you had me around, by golly. Oh, sorry to bother you. Bye. Why? You look awfully sad. Oh, hello, Jillian. It's just that, well, I can't find myself. I'm defined by a differential equation, y prime equals f of y and t, but nobody's solved it. Oh, what a shame. But wait, f of y and t, you say? The function f is a good friend of mine. I'll go get him, and maybe we can help you out. Fred, this poor function here says he can't find himself. He says he's defined by a differential equation you're involved in. Y prime equals f of y and t. Do you think you could help him out? Well, why, I'm pretty sure it can't be solved explicitly. But you know, it's all the rage these days to approximate yourself numerically. Oh, wow! With a computer? Well, I guess that could work, especially if it's the only option. How will we go about it? Excuse me, I couldn't help but overhear that you need a numerical approximation of a differential equation. Well, I thought of the first one there is. Oh, hi, Mr. Euler. You did all those great things with the number e. Do you think you could help us with this too? Of course, Jill. Now, why? It's you that needs to be approximated, right? Well, here's how we'll do it. Pick an initial condition, any initial condition. 2. Okay, we'll start at 2. What size of time do we want? Size of time? For numerical approximations, you have to discretize the time variable, I'm afraid. Now, what size? A tenth of a second? Okay, can do. Now, starting at 2, we find your slope there. Fred, slope at 2? F of 2 and 0 is 1/2. Very good. 2 plus the change in time times the slope is 1/2 of a tenth of a second. So your next point, y sub 1, is 2.05. But this will take forever. No. We'll just have a computer finish the rest. All right, feed in the codes now. Beep, beep, beep. Just a moment, Mr. Euler. Beep, beep, beep. Oh, wow! Wait a second, Mr. Euler. From your method, it sounds like... Wait a second. How do we know that that's really what y looks like? From your method, it sounds like every iteration will get worse and worse because you're basing it on a previous approximation. Y surely isn't made of straight lines like that picture. Got to run. I see some complex variables over there. What a hunk. Oh my gosh. Wow. Gosh, at least I've got something. But you're right, Jill. How do I know it's really me? We'll have to figure out the errors, why? Let's see. If he's approximating you with straight lines, that's just like using only the first term of your Taylor expansion. So the error at each step must be the second term of your Taylor expansion about t plus delta t. That'll be delta t times the local truncation error, delta t y double prime of psi over 2.
Somebody around here looking for me?
Oh, there you are, local truncation error. We just wanted to check that you weren't too big.
Well, it's not me that you care about. It's global error.
Global error? Global error? I wonder what that could be. Yeah, I wonder what the global error could be. He's a big global error, but I bet we can bound him. Fred, you said that the local truncation error is proportional to the time step and to the second derivative, right?
Yep, that's right.
Why? Do you know where your second derivative is?
Not sure.
But I think it's only about as far as eastern Connecticut. Great, that's not too far away. Let's put this upper bound of the global error before he wakes up.
Yay! Now, if only there might be a way.
Whoops! Oh, Fred!
Now, if only there might be a way to make the error even smaller. The error is awfully big. I guess I would have to, it won't get much smaller even if I take really small time steps. That's right, it's just a first order method because it only scales linearly with delta t.
Hey! There go Mr.s Runge and Kutta. Hey! Runge and Kutta, come back!
What is it, my dear?
Can you help us approximate this function y a bit better? Mr. Euler's method didn't do very good job. We just got this huge error down here.
Oh my, that is a problem. By all means. Now, Euler was trying to use straight lines to approximate you.
Yes, he was.
Well, we'll use an integration technique to integrate y prime equal to f of y into t, and we'll use an integration technique that's a bit like Simpson's rule to approximate you with curves. Just need to take a few measurements here. All right, pretty good. Now, what additional condition would you like?
Oh, 2, please.
Certainly. Let's put this into the computer. All right, I have to feed in the codes there. And a few moments. Beep, 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 beep. Beep, 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 beep. Ah, here you are. Much better approximation.
Oh, wow! It looks so much more like me. Thanks, Runge and Kutta.
Oh, call us RK.
Bye, RK.
Bye, guys.
Well, that looks like it. Thanks, Jill and Fred.
Oh, that's not all the possibilities, though, Wyatt. If I were harder to evaluate, you might do better with the multi-step method, where you take multiple approximations. Oh, well, what you want to do is you want to use the previous approximations, several of them, to find the next approximation, and that way you don't have to have as many function evaluations.
Okay, I'll keep that in mind.
Oh, and one last thing. You're not stiff, are you, Wyatt?
No, I don't seem to be.
Well, if you ever do get older and stiff, you should try an implicit or backward step method, because otherwise the approximations might blow up.
Thanks, Fred. Thanks, Jill.
Thanks for helping out that function, Fred.
Sure thing, Jill.
Now let's go see if there are any other